Dear students, I am Dr. Tamrakar from Bharati College of Engineering and Technology, Durg. I am teaching food machinery in BE 5th semester. Today we will solve one numerical. An inward flow reaction turbine has external and internal diameter as 1 meter and 0.5 meter respectively. The velocity of flow through the runner is constant and is equal to 1.5 meter per second. Determine first discharge through runner and second width of turbine at outlet if the width of turbine at inlet is 200 mm. Here the data given are external diameter d1 equal to 1 meter and internal diameter d2 equal to 0.5 meter. Then velocity of flow at inlet and outlet, that is Vf1 equal to Vf2 is equal to 1.5 meter per second. 1.5 meter per second has been given. Then width of turbine V1 is given 200 mm. Width is 200 mm. So converting this into meter, that is 0.2 meter. 0.2 meter. Then let the width of outlet is V2. Width at outlet, width is equal to V2. Then Q equal to pi D1 V1 Vf1 equal to pi into 1 into V1 is 0.2 into Vf1 is 1.5. So this Q discharge comes 0.9425 meter cube per second. Also, as we know, pi D1 V1 Vf1 Q is same, discharge is same in inlet and outlet. So this is equal to pi D2 V2 Vf2. This is constant. So putting the value here, this is 0.9425 equal to pi into 0.5 V2. What about B2? B2 we have to calculate, or we can slightly modify this by cancelling this pi with pi, Vf1 with Vf2, both are same. So this D1 B1 equal to D2 V2. So here B2 equal to, using this sign, B2 equal to D1 B1 by D2. So this is 1 into 0.2 by 0.5. So the value of B2 comes here is 0.4 meter, that is equal to 400 mm. 400 mm. We'll solve one more numerical. An inward flow reaction turbine has external and internal diameter as 0.9 meter and 0.45 meter respectively. The turbine is running at 200 rpm and width of turbine at inlet is 200 mm. The velocity of flow through the runner is constant and is equal to 1.8 meter per second. The guide blade makes an angle of 10 degree to the tangent of wheel and the discharge at outlet of turbine is radial. Draw the inlet and outlet velocity triangle and determine the absolute velocity of water at inlet of runner. Second, the velocity of whirl at inlet. Third, the relative velocity at inlet. Fourth, the runner blade angle. Fifth, width of runner at outlet. Sixth, mass of water flowing through the runner per second. Sixth, head at inlet of the turbine. Seventh, power developed and hydraulic efficiency of the turbine. These all questions asked. This question, if asked in the exam, then that will be for all 13 number or 16 number. This type of questions may be asked. This is a long question. Here the data given for the question is external dia D1 is given 0.9 meter. Internal dia D2 is given 0.45 meter. Speed N is given 200 rpm. Width at inlet B1 is given as 200 mm, that is equal to 0.2 meter. Velocity of flow Vf1 equal to Vf2. Vf2 is equal to 1.8 meter per second. Guide blade angle alpha is given 10 degree. Discharge at outlet is radial. Discharge at outlet radial. That means beta equal to 90 degree, and that also means VW2 is equal to 0. Tangential velocity of V at inlet and outlet are U1 equal to pi D1 n by 60, and putting the values here, that is pi, and value of D1 is 0.9 into n is 200 rpm, that is by 60. So this U1 comes 9.424 meter per second, and U2 can also be calculated by D2n by 60 equal to pi into 0.45 into 200 is divided by 60 equal to 4.712 meter per second. Now we have to calculate absolute velocity of water at inlet of the runner V1 from the velocity triangle. So here we have to make velocity triangles. So here the blade is like this, and velocity triangle at inlet. We have to make the velocity triangle at inlet, and this one is the velocity triangle at outlet. Velocity triangle outlet is this, because here velocity of one at outlet is radial. Here this is angle phi, this is U2, this is VF2, VR2, this is V2, and this is also VF2. This is beta 90 degree. Beta is 90 degree, and this is the runner here. This is the runner, and here the different blades are arranged in the same manner. This is the inlet triangle. In the inlet triangle, this is tangent line. This is angle alpha, this is angle theta, this is U1, this is VW1, this is VF1, VR1, this is V1, this is tangent, and here this is tangent line here. This is runner. This is the runner. Okay. Now, absolute velocity of water at inlet of the runner, that we have to calculate the V1 sin alpha equal to VF1. Here this VF1 equal to V1 sin alpha. Okay, this is for sin alpha angle. So here V1 equal to VF1 by sin alpha, putting the values 18, this is 1.8 by sin 10. You have to check this, whether this is 1.8 or 18, because in some books it has been given 18, and in different book it has been given 1.8 meter per second. So I am calculating by taking 1.8. So this value we have to check by calculator, comes 10.365 meter per second. Next we have to calculate velocity of one at inlet VW1 equal to V1 cos alpha. Here this is V1 cos alpha, VW1 equal to V1 cos alpha, putting the values here 10.365 cos 10 degree. So this is 10.207 meter per second. Relative velocity at inlet VR1 we have to calculate for this, it is V1 square equal to V1 square plus VW1 minus U1 square VR1. Here this is VR1. This VR1. So this is equal to V1 square VW1 minus U1 means this one, and VF1 square. This is VF1 square. VF1 square. In some book it has been given V1 and somewhere it has been given VF1. So I was checking that this is 1.8. The value has taken 1.8 meter per second. So putting the values here, square root 1.8 square plus 10.207 minus 9.424 square. U1 we have calculated earlier. So the value of VR1 comes 1.968 meters per second. So here calculating the runner blade angle means we have to find fourth runner blade angle. Runner blade angle theta and phi. Tan theta equal to VF1 by VW1 minus U1. Putting the values here, 1.8 by 10.207 minus 9.424. So this value is 2.298. So the angle theta is 66.48 degrees, or it can be represented as 66 degrees and 29 minutes. This is the angle theta. And for calculating the angle phi in the outlet velocity angle, tan phi equal to VF2 by U2. Putting the values here, VF2 is also 1.8 and U2 is 4.712, that is equal to 20.9 degree. So phi equal to 20.9 degree or 20 degree and 54.4 minutes is the value of phi. Next we have to calculate width of runner outlet B2. As we know, point from the continuity equation, pi d1 b1 vf1 equal to pi d2 b2 vf2 or d1 B1 equal to B2, B2 equal to P1, B1 by B2, that is 0.9 into 0.2 by 0.45. So this B2 comes 0.4 meter equal to that is 400 mm is the width at outlet B2. Then next, mass of water flowing through runner per second. Mass of water flowing through runner per second comes from the discharge. As we know, discharge equal to pi D1 B1 VF1. Putting the values here, pi into 0.9 into B1 is 0.2 and VF1 is 1.8. So here this charge is 1.01 1.0178 meter cube per second, and mass equal to rho into Q, that is rho AB replaced by Q, and rho for water is 1000 and 1.0178. So the mass comes 1017.8 kg per second. Next, head at the inlet of turbine. Head at inlet of turbine. H minus V2 square by 2G equal to 1 by G V W1 U1 plus minus V W2 U2. Putting the values here, as we know, VW2 equal to 0, so this is equal to 1 by G VW1 U1. So H equal to 1 by G VW1 U1 plus V2 square by 2G. Putting the values here, this is 1 by 9.81 into 10.207 into 9. Value of U is 9.424 plus 1.8 square, 1.8 square by 2 into 9.81. So here the value comes, value of H is 9.97 meter is the head in this question. And some more points are there. So basically this type of question is a long type question for 16 marks. Next, point 8 is power developed. Power equal to work done per second on runner, work done per second on runner, by 1000, that is on kilowatts, that is equal to rho Q V W1 U1 by 1000, putting the values here, value of rho equal to 1000 for water, this is 1000, and Q we have calculated 1.0178 into VW1 10 to the 7 into U1 9.424 by 1000, cancelling this 1000, so this comes 97.9, and this is in kilowatt because this is divided by 1000. And last, hydraulic efficiency. For getting the hydraulic efficiency, this is VW1 U1 by GH, putting the values here, this is 10.207 into 9.424 is divided by 9.81 into 9.97 as we have calculated earlier. So this is 0.9834, that is 98.34% is the hydraulic efficiency of this type of turbine. So as this question is a very large question, and it has been asked sometimes for 16 marks, and you solve many more questions like this from the question paper. Thank you.